Good afternoon. How's everybody doing out there?
Awesome.
Welcome. So, hope you're all having a fantastic time. NDC London 2023, day one. For the next hour, I am going to tell you stories about electricity. Now, I have kind of a nice, I don't really have a job. I just do cool things, and sometimes I get paid for it. And a big European company, the company who build the control software for most of the power grids in the European Union, got in touch with me last year and said, we're doing a developer conference, can you do a keynote for us? And I was like, yeah, what do you want it to be about? And they said, can you do a talk about electricity? And I'm like, you're the experts. Like, you're supposed to know all the electricity stuff. They're like, yeah, but really, we don't really do electricity, we do software. I was like, well, if you're doing software, you have to, do you have any analog software that runs on steam power? And they're like, you know what we mean. So I got the chance to, geek out and dig into all of these cool and weird details about electricity and all the different ways that technology, software, we apply electrical power in different ways. And so that's kind of where this talk came from. And I put it on the pitch for NDC London, and I put a talk next to it, which was a technical talk about how to write JavaScript, and the rest of the committee went, we don't want to listen to you talking about JavaScript, do the thing with the lightning in it. And so this is sockets, sparks, and magic smoke. And this is me. I'm not on Twitter, well, I am on Twitter anymore, but I do all my fun chat now on hachyderm.io because I've joined the Fediverse. The future of the web is decentralized, but it has nothing to do with cryptocurrency. It's about running lots of little Twitters that aren't birds, they're elephants, and they're all chatting to one another. And you know the old thing about who would win in a fight between one elephant-sized bird and 1,000 bird-sized elephants? I'm betting on the elephants. I run Ursatile, I'm a Microsoft MVP. I run the London.NET user group when we don't have to cancel it because of train strikes and venues pulling out on us. And I once invented a programming language just for all of you folks out there who really want to apply for those rock star programmer jobs that they still advertise once in a while on LinkedIn. And we are going to talk about electricity. Because without electricity, we wouldn't have any software. We wouldn't have any hardware. We wouldn't have any mobile cellular networks. We wouldn't have any internet, any YouTube, any .NET and Lambda and cloud and serverless and all this kind of stuff. And so we are going to work our way up the scale of electrical power. And we are actually going to start here. We are going to start at 0 because it turns out you can do computing without using any electricity. There is so there's a bit of controversy about whether prehistoric or ancient civilizations had electricity or not. There is an archaeological find, it's a thing called the Babylon battery, which a bunch of people found and they went, this is really exciting. Look, it's got an outer chamber and it's got copper, and if you put paper in here, then it becomes a battery, and they could use it to electroplate things in ancient Persia. And everyone went, have we found any electroplated things from ancient Persia? And I went, well, no, and they're like, it's probably not a battery. So we don't think that there was, ancient civilizations had batteries, but they did have computing devices. This is a fragment of a thing called the Antikythera mechanism. It was found in a shipwreck off the island of Antikythera, which is in the Mediterranean off the coast of Greece. And it basically came up as a corroded lump of metal that a bunch of archaeologists kind of started looking at. They x-rayed it, and they discovered that inside this thing were mechanical gears and cogs and things. This was a computer. This was an ancient Greek computer that was used to calculate the phases of the moon. It had little gears in it that would tell you when the next solar eclipse was likely to be. And the prevailing theory is that they used this to predict when it was time to have the Olympics. So this is hundreds, probably thousands of years before the advent of electricity. Now, this idea of mechanical computers that don't use electrical signaling, kind of came to a peak with a guy called Charles Babbage. This is so Babbage designed mechanical computing systems. This is a photograph of a reproduction of part of a system he designed called the analytical engine. Now, he designed computers that were never built. During his lifetime, he died in about 1840, I think, and during his lifetime, one, he didn't have the money to fund the construction of his designs. Two, the engineering precision did not exist to actually allow them to realize it. This was a project that came out of the Science Museum in London in the 1990s, and they built a working replica of a simpler system, a thing called the difference engine for calculating logarithms. He designed a general-purpose computer called the analytical engine, which would run programs punched on cards that were used to run mechanical looms. And this thing, at the moment, a team at the Science Museum is digitizing all of his notes to see if they can get a blueprint to see if maybe they will be able to build a working replica of his analytical engine. So give it another 10, maybe 15 years, there might be a general-purpose Turing-complete mechanical computer ticking around in a university or in a museum somewhere in the world. But mechanical computing actually went on a lot longer than any of us think. This is a thing called the Norden bombsight. It's a mechanical bomb site used for dropping bombs. It was invented in the 1930s, and it was used by European and American air forces right up until the end of the Cold War, the sort of 1980s, early 1990s. The Russian, or the Soviet, and later the Russian space program, they were using mechanical gyroscopes to navigate space capsules until 2002. Now, at the moment, there's not a huge amount going on to do with mechanical computers. But we have a rover on Mars. Human beings have a click, 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 click. Come on, clicker, you can do it. There we go. So Mars, as far as we know, has no organic life, which means there is a planet in the solar system that is populated entirely by robots, which is kind of cool. And there are, I think, 7 probes have been sent and have been roaming around on the surface of Mars. Some of them are still going. They even put a helicopter up there last year. And NASA would love to do the same thing and land a probe on the surface of Venus. There is a problem. The atmosphere on Venus is a mixture of carbon dioxide and sulfuric acid. The temperature on the surface of Venus is 460 degrees Celsius. We got any scuba divers in the room? Any of you ever done scuba on holiday? Yeah, the pressure at the surface of Venus is equivalent to scuba diving a depth of 1 kilometer. Surface pressure is 90 bar. Now, do any of you fancy building an electrical circuit that is going to survive at 90 atmospheres of pressure, where the atmosphere is 460 degrees sulfuric acid? We have landed things on the surface of Venus, and you know what happened to them? They dissolved, and they melted. We cannot build any kind of electrical circuit that is going to function reliably in those conditions. But there is a team at the Jet Propulsion Laboratory at NASA who are like, all right, can't use electricity, can't use radio, can't use transmissions. We're going to do this. It's a prototype for a wind-powered autonomous rover. The thing in the middle, this thing is about this high. It's about 1.5 meters high. This is artist's impression of the design they're working on. The thing in the middle is a giant wind turbine. Now, they have no control over this thing. They're going to drop it on the surface of Venus, if this project goes ahead. And as the wind blows, it's just going to roam around the place and poke stuff and measure wind speed and measure temperature. And if you look closely at this picture, the thing on the top that looks like 4 CDs, those are optical semaphore plates that are reflective to radar. So there's a satellite in orbit around Venus, and when this thing kind of gets onto a bit of soft ground, one of the gears is going to move one of those slightly, and it'll reflect a particular radar pattern, and the orbiting satellite can go, all right, we have no control over it, but we know where it is, we know which way it's moving, we know how fast the wind is blowing, we know what the soil conditions are like down there, we know the temperature, all this stuff using completely mechanical circuits and mechanical devices, which you have to admit is the most badass steampunk thing you have ever heard of. But they're still working on that. So let's get back to the idea of electricity. Now, electricity is useful because of 3 things that we human beings can do with it. One of them is the reason why this guy's famous, and for a long time appeared on the old British 20-pound note that was in circulation for about 20 years. We can turn electricity into movement, and we can turn movement back into electricity. The guy on the banknote is Michael Faraday, who discovered electromagnetism. Now, this is how most electrical power generation works. We have spinning turbines, we put movement in from steam or burning coal or water or any number of things we're going to talk about. We get electricity out the other side too. We can put electricity in the back. We get motion, we get motors. We also, this is the most significant discovery in the history of humankind, because it is also how heavy metal works. Because the pickup in an electric guitar, that thing in the middle of the picture, that's a couple of thousand turns of copper wire, And when you pluck the string on an electric guitar, the steel string moves through a magnetic field, and it induces a current in those coils that we feed into an amplifier, and heavy metal comes out the other side. Really, really important engineering principle. The second thing that we can do with electricity is we can turn it into radiation, and we can turn radiation back into electricity. And it turns out there is really only one flavor of radiation, or one kind of radiation. It just comes in different intensities, different wavelengths. Way down at the bottom of the spectrum here, we have gamma rays. These are very, very bad for you unless you're in a Marvel comic book. In real life, no, you don't end up as a superhero, or your teeth and your hair fall out, and then you die. Then we get up a little higher. You ever fallen off your bike? You've fallen over skiing. You've gone for an X-ray. Radiation. Put electricity in the metal, radiation comes out, they use it to take a picture. Yep, there you go, you fell over and you broke your leg. We get into the ultraviolet part of the spectrum, the awesome day glow effects you get on nightclubs and bad water slides. We have the visible spectrum. Blue, orange, yellow, red, all of the colors that our eyes can see. Top end of that, we have infrared, which is where it starts turning into heat. Just above that, we have Wi-Fi, the 2.4 gigahertz band. We also have microwave ovens in the 2.4 gigahertz band. Have any of you ever lived in a shared house where the microwave was next to the Wi-Fi point? And every time someone goes to heat their pasta, all your YouTube stop working? Yeah, that's why. Exactly the same radiation in the same spectrum. Wi-Fi, 2.4G, microwave radiation, same part of the spectrum. We get up a little higher, and we get into radio. AM, FM, long wave, medium wave. And radio is the second most important invention in the history of humankind, because it means that you can have heavy metal without having to be in the same room as the people who are making the heavy metal, which was a big, big innovation. And the third thing we can do with electricity is we can store it. Now, you go to a store, you buy a Duracell battery, you put it in your camera, you put it in your PowerPoint clicker like this one, or the remote control for your TV. It works once, right? And it works for a little while, and then eventually it stops working, and you recycle it responsibly, or you throw it in the trash. Now, it's probably occurred to some of you, hey, what if I put the electricity, can I put the electricity back in the battery? These kind of batteries, you can't. They don't like that, because what's going on inside one of these batteries when you buy it is you have what's called a cathode. This is made of magnesium dioxide. There is an anode, which is a little needle made of zinc running down the middle of this thing, and there is an electrolyte, potassium hydroxide. Who knows what battery tastes like? You ever had the thing where you've got a piece of electrical, the battery has burst or it's leaked, and you're trying to fix it, and you've got to strip the wire with your teeth, and you're like, gah. That is potassium hydroxide, that horrible, sour, kind of burning taste. And when you buy a battery from the store, what is going on with it is this, the collector in the middle, this is the brass pin that actually gets the current out. This thing is in a steel casing, and it is absolutely full of atoms. And the atoms move from the cathode, and when you start a circuit flowing, all those atoms go, hey, let's go over there, look at that. That looks awesome, and they start to move. And when they move, they generate a tiny, 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 tiny amount of electricity, but there are lots of them. A couple of 100 million, billion of these atoms, and every time one of them moves, it generates current which flows through. Once all the atoms have relocated, that's it. Battery's finished, no more electricity, recycle it. Now, this is one kind of electrochemical reaction. This one is not reversible. If you pump power back into a Duracell battery, it'll get hot, it'll expand, and it might even explode if you're very lucky. But it's not the only electrochemical reaction. The lead-acid battery in your car, that one doesn't care. That's lead oxide with sulfuric acid between the two. You pump the power back into it, it just switches it, so the lead becomes the lead oxide, and the lead oxide turns back to lead, and the oxides basically just kind of slosh backwards and forwards. That's how car batteries get recharged. Now, battery technology has, the advances in battery tech within my lifetime are absolutely unbelievable. When I was a kid, electric vehicles were, some of you probably recognize this, it's milk float. Top speed, 20 kilometers an hour. Maximum range, 100 Ks, that's about, what, 70 miles. And after it had finished delivering all the milk to your neighbors, it had to go back to the depot to recharge for 16 hours before it was ready to go out tomorrow and deliver a little bit more milk. Today, we have electric cars that can do hundreds of kilometers on half an hour of charge, top speed of about 180 Ks. Now, we can do some astonishing things with batteries and energy storage. The state of the art on this has evolved massively. Could we store enough electricity to power a city? We're going to come back to that later. But we are going to talk now. We looked at three capabilities of electricity. We can use it to create motion, we can use it to create radiation, and we can store it. Now, I'm talking to you right now. My voice is creating pressure waves in the air. This little microphone here is picking them up and amplifying them. Pressure is reaching your eardrums. And when it does, your eardrum is turning the signal from my voice, the pressure from my voice, into a tiny, tiny electrical current that is getting sent up to your brain. Now, the human nervous system works on about 10 millivolts of electricity. And it doesn't work like a conventional wire. The cells in your nervous system, it's more like a Mexican wave. A little cell in your ear goes, ooh, I heard a noise, electricity. It charges the cell membrane. And the one next to it goes, ooh, charge. I'm going to charge my cell membrane. And this propagates through your body into your brain where something goes, hey, that guy's talking about electricity. And we come full circle. Now, one of the first people to do extensive study into the way electricity works in biological systems was this guy, Luigi Galvani. You probably heard the expression galvanized. It's a way of coating things with zinc to stop them rusting. And this is a little bit icky, but what Galvani did, one of his experiments, is he took dissected animals and he applied electricity to frogs' legs, is the famous example, and they twitched. And he came up with this conclusion that the thing that was making the muscles move was an electrical signal. This was the basis of physioelectromagnetism. Now, one of the first people who read a preprint of his paper was Mary Shelley. This was about 3 years before she wrote Frankenstein, in which the Dr. Frankenstein and his nameless monster, he puts together a monster out of, bits of cadavers and stuff and then uses the power of lightning to reanimate it. So biological systems do weird, cool things with electricity. I did actually break my leg skiing a couple of years ago, and I got one of these. I got an electroshock therapy thing to help kind of rebuild the muscle after I had my leg glued back together. And this was really strange. You kind of put these electrodes on your leg like this, you sit and watch TV, and after half an hour, one of your legs is really tired, because it's just been the muscles in it are going twitch, 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 twitch every time you get this little electric shock in it. Now, one of the most interesting applications of electrophysiology is this. It's Pacemaker. Some people's hearts don't beat regularly, and some people's hearts do beat regularly, but they don't beat fast enough to give enough oxygen to all the parts of that person's body. And so we have come up with a way of running. You look closely, you can see these two wires actually running into the heart. And all they are doing is they're using a tiny electrical signal to regulate the beating of a human heart. Now, the battery in a pacemaker has about as much capacity as the battery in your phone. Battery in your phone has enough power to watch YouTube videos and send WhatsApp messages for 10 hours, or to keep a human heart beating for 10 years, which is probably just as well, because replacing the battery in these things, one, they got to cut you open, and two, when they take the battery out, your heart stops beating until they put the new one in. So this isn't the genius bar kind of, can you put a new battery in this thing? It's a fairly substantial procedure. So we can do cool things with biological systems using very, very tiny amounts of electricity. But we've also done cool things with artificial systems and mechanisms. This is Voyager 1. Voyager 1 was launched in the 1970s, and at the moment it is still operational. Launched in 1977, left the solar system in 2012, August 2012. It is still out there, and it is still transmitting. Now, on board Voyager 1 and Voyager 2 is a thing called a radiothermal isotope generator, radioisotope thermal generator. It's a chunk of plutonium connected to a thermocouple, which is a thing that turns heat into electricity. That's how this thing works. There are 3 of these on board. They give out about 400, or they used to give out about 400 watts of power when they were new. These 2 spacecraft have been flying through space for longer than I have been alive, and they are slowly beginning to shut down because the half-life of the plutonium means it's not quite as warm as it used to be. So it's not putting out quite as much power as it used to, which means that NASA are slowly shutting down various systems on board Voyager. Now, some of you may have seen this picture. It's called the pale blue dot. It was taken by Voyager 1 in the 1990s from outside the orbit of Saturn. This is us. That is planet Earth hanging in the darkness. This is probably the most expensive selfie ever taken, right? But Voyager was built in the 1970s. We didn't have iPhone cameras in the 1970s. We didn't have charge-coupled devices, webcams, CMOS, all this stuff we take for granted today. Voyager took this photograph using a thing called a Vidicon tube and stored the picture on tape. There is a tape deck in space right now, 2 of them in fact, which was specially built for this. It's magnetic tape. Now the 2 reels here, they had to go in opposite directions, because if they went in the same direction, it would mess with the gyroscopes and Voyager would have gone off course. Voyager 1 has been shut down. The tapes on it are no longer working. Voyager 1 is just pinging back an occasional, hey, I'm still awake out here message. The tape deck on Voyager 2 is still working. And we know this because NASA publishes the spaceflight operation schedule for Voyager on their website every couple of weeks as a PDF. And this is the operation schedule for right now, January 2023. This is Saturday, January 21st, which is 4 days ago. And there you go. That's the playback instruction. The 1970s tape deck that is flying through outer space beyond the reaches of the solar system. On Saturday, they sent a message going, hey, back it up, replay the tape, let's see what we got. They don't have much. There is not very much out there for Voyager to be taking pictures of. But this 1970s tech is still out there. It's still working. And the reason we can pick it up, if you look at Voyager, the main feature you'll notice is this thing. It's the main radio antenna dish on the back of it. It's about 3.5, 4 meters across. You can see a picture of it there with one of the engineers who worked on it. Now, Voyager's 23 billion kilometers away from Earth. It takes 21 hours for those radio signals to reach us. The total transmitting power of that transmitter there is 23 watts. It's about as bright as the light bulb in your refrigerator. And we can pick it up from the other side of the solar system because we have this, NASA's Deep Space Network. It's 3 radio telescopes. There's one in California, there's one in Spain, and the other one is Parkes in Australia. Now, there's, I don't know, did you see Tom Scott did a video about Parkes last week? And one of the things he said in that video, one of the things that the person he's talking to said in that video, if you take a feather and you drop a feather onto a carpeted floor, the noise of that feather landing on the carpet puts out more energy than all the signals we have ever received from all the radio telescopes that we have ever built. If you took your cell phone and dropped it on the moon, that would be the brightest thing in the sky to one of these telescopes. They are unbelievably sensitive. So we are still picking up signals from Voyager. It's out there. It's getting weaker. Eventually, probably within the next couple of years, it's going to shut down. But you come across the idea of a light year, right? Like if light flies into space in a straight line for 1 year, that distance is 1 light year. Humankind is nowhere close to being able to send anything a light year. Or we are, we only just got started, you know. But if Voyager makes it to November 2026, it will cross the 1 light day threshold. It will be more than 24 hours signal away from Earth. I think that's a pretty cool milestone. And when it happens, if it survives that long, we will find out about it through the medium of electricity because it will pop up on a mobile phone or on a news feed or on a website or somewhere. And now we are into the bit of the electrical kind of voltage range, which I call the user-friendly electricity, the handy stuff that comes out of the wall. Now, did you know you can actually tell quite a lot about a country by the shape of their plug sockets? Like, you know, their attitude, how well adjusted they are. Like, these are the plug sockets they use in Denmark, and these are the plug sockets they use in the United States. And, and I put this on Twitter, and someone said, oh, that's not even the best one. In hospitals in Denmark, they have ones that wink at you. Now, plug sockets are different shapes. You travel around the world, as a lot of people in this room do, I know, and you're constantly looking out for adapters, and how do I plug my laptop into this wall? And a lot of the devices we use now, they can cope with a range of different voltages. They can't necessarily cope with a range of different shapes. So it's okay, you can always improvise, you know. Don't do this or you will probably die. But it's not just the shape of the plug socket that's important. We also have different voltage standards. The UK, the European Union, quite a lot of basically the bits of the world that were fairly recently invaded by the British tend to use around 220 volts. North America uses 110. And actually, North America uses 110 because they got there first, because they rolled out electric lighting early enough that they hadn't standardized on a 220-volt system yet. So they were the early pioneers, and now they're stuck with that. But there is a wonderful theory about the way electric devices work, microchips, transistors, these kinds of things, which is that they are full of magic smoke. And when they make them in the factory, they take the smoke and they trap the smoke inside the chip and they seal it up. And if the chip gets too hot, what happens is it cracks and the magic smoke comes out. And after that, it doesn't work anymore. Now, many, many years ago, my first-hand experience of magic smoke was a computer that looked like this. AMD K6, it had I think a 4 gig hard drive and 64 megs of RAM and Windows 95. And it was that point in my life where I had enough money for one computer, but I couldn't possibly afford another one. And I was constantly tinkering and poking around this thing. And one day I was poking around the back, putting in a sound card or something, and I accidentally bumped this switch from 220 to 115. I didn't notice, and I plugged it in. And I put 220 volts through a power supply that was expecting 115. There was a lot of magic smoke and a very big bang, and after that, the computer didn't work anymore until I wombled a new power supply from somewhere. Now, some devices, if we give them too much voltage, they explode and they don't work anymore after that. Sometimes, though, putting too much voltage through something is actually a good idea. If you go into your computer's BIOS, there will be a little setting in there somewhere which allows you to control how fast it's going to go. And raw clock speed, who was in Richard Campbell's talk this morning? He's talking about Moore's law, and he's talking about the numbers of transistors we can put on chips and stuff. And one of the measurements of computing power is just raw clock speed. How many times per second can your computer do a single calculation? And we routinely have, 2,600, so 2.6 gigahertz, that 2.6 million operations per second. That sounds like a lot of instructions, right? Now, let's say we want to sit down and we want to play Stray. Now, if you're running Stray on a kind of 4K monitor, you're talking about sort of, 4,000 by 12,000 or 1,200 pixels. It's going to be probably about 1 million pixels on the screen, about 240,000 or so. And you want to run that at 60 frames per second, which means each pixel on your screen is going to be lucky if it gets, I think we get a bit to a point where it's about 17,000 operations per second per pixel. We need to do that 60 times. And then you take into account, well, you've got to do a lot of vector and matrix arithmetic to draw a game like this. You've got to calculate lighting effects. You've got to calculate fog and distance. And also in the background, the computer is also checking your email, and it's running the audio, and it's running the network stack, and it's probably doing something stupid with Microsoft Teams in the background. Suddenly, 2.6 billion, jillion, million operations per second doesn't look like very much. And so the question comes up, can we make them go faster? Now, a couple of years ago, I built a gaming PC for my brother. We wombled some bits, and we bought a power supply and a hard drive. We ordered a lot of parts from eBay to put this thing together on the cheap. We put it all together. He came down to my place for the weekend. We screwed it all together. We set it all up, ran a burn-in test, 24 hours, rock solid, everything's fine. He took it home, rings me a couple of hours later, it's crashed. I got to visit him in Bristol, where he's living at the time. Switch it on, it crashes. We switch it on, it crashes. Like, all right, I'll take it home and look at it. I take it home, take it apart, look at all the bits, run another burn-in test. Absolutely rock solid. He takes it back, crashes. I'm like, why does it only crash in Bristol? So I go up and I stay for the weekend. We take it apart. I take the tools and everything. We take the thing apart. We run a burn-in test, absolutely rock solid. Put it back together, put it under the desk. It crashes straight away. I'm thinking, this is the weirdest thing that I've ever come across. It just keeps doing this. By the way, keep yourself on your toes, put a blue screen of death in all your PowerPoint presentations. So when it comes up, you don't know if it's a real one. Eventually, we caught it. We figured out what had happened because we caught just before it crashed really, really hard, we got a thermal overload warning. Now, the motherboard we'd bought on eBay was old and it was a little bit worn out. And it had a great big, huge, heavy heatsink on it. And whenever we had been running diagnostics, we had the computer up on a desk, on its side, with the motherboard flat and the heatsink vertically sat on it. Soon as we thought it was good, case back on, put it on its side under the desk, and the heatsink was pulling away from the CPU by about 1 millimeter. And that was enough. That was enough that within 5 minutes, the CPU got to 98 degrees Celsius and just went, I'm not playing anymore. Now, cooling is a massive problem. We want to put more voltage into CPUs because more voltage makes them go faster. And we want faster, we like faster. But more voltage also means more heat. A modern Intel CPU, just sitting doing not very much, is ticking over at about 60, 65 watts. This is like an old-fashioned incandescent light bulb, sealed in a metal box, and you need to keep that cool, otherwise you're gonna have a problem. You start encoding video, you crank up a game, it's gonna start pulling 150, 200 watts. That's like 3 incandescent light bulbs in a little metal box, and you need to keep that thing cool. First computer I ever had didn't have a heatsink. By the time mid-90s came around, I had a 486 with this kind of little metal hedgehog on the top. Then we got the big metal hedgehog with the fan for a hat, and then we got the giant, enormous metal hedgehog with the huge exhaust fan on the back like a vacuum cleaner. Now, the world record for raw CPU clock speed was not achieved with a supercomputer or a one-of-a-kind prototype or anything particularly fancy. It was achieved with one of these. It's an AMD FX processor. You can buy this on Amazon right now for about 120 quid. And in 2014, somebody calling themselves The Stilt submitted this verified screenshot to the CPU-Z validator site, 8,722 megahertz. 8.7 gigs. They took that, you can see a couple of the details on there. So they took an off-the-shelf CPU, they cranked the voltage up to about 2.1, 2.2 volts, overclocked the hell out of it, and put the whole computer in a bath of liquid nitrogen. That's how they got it stable at this speed. Now, that's a little extreme, like, liquid nitrogen is not really stuff you want to be messing around with terribly much. We have this thing, Richard was talking about this morning, Moore's Law. Now, Moore's Law for a long time was computers get faster, double in speed every 18 months. But what Gordon Moore actually said is the number of transistors we can put on a single piece of silicon is going to double every 18 months. Now, for a long time, that correlated exactly with clock speed, because more transistors meant it went twice as fast. We are getting to a point now where we are hitting the buffers at the end of physics, and we cannot push them any further. Mechanical hard drives, state-of-the-art staple for years and years and years. We got incredibly good at building these things. And these use little tiny magnetic particles. You've got a disk that's spinning at 15,000 revolutions per minute, and you've got a head on the end of it that's watching this disk coming around and going, that bit there, 3, 2, 1, grab it as it goes past and see if it was a 1 or a 0, and then off we go again. And, for a long time, this was the state of the art in storage. These things are fantastic unless you drop them or bump them or knock them, or they just get unhappy, or they get too hot, or they get too cold. They are temperamental little buggers. So we went, well, what if we could have memory that didn't lose all its contents when you disconnected the power? And this is impossible, according to the rules of classical physics. You cannot do that. But then quantum physics comes along and goes, hang on, we got an idea. We have quantum tunneling. Quantum tunneling is a way of electrons ending up being in a place where they weren't supposed to be, and once they get there, they get stuck. And this is how solid-state drives work. This is how thumb drives work. This is how SD cards work. They have, so every bit on your SSD hard drive is a quantum gate semiconductor, which uses quantum physics and exploits the fact that the behavior of electrons under certain high-energy conditions is non-deterministic, and they can end up in places where there wasn't actually a circuit between where they started and where they ended up. I've sometimes described this as like if you give your children too much sugar and then put them in the kitchen, they can get from the kitchen to the living room without opening the door. That's how quantum tunneling works. For hard drives and storage, it's fantastic. For CPUs, it is a problem. We've got down to a point where we can manufacture CPUs where the distance between these tracks is 10 nanometers is common now, 7 nanometers, 5 nanometers is kind of prototype, and as Richard said this morning, somebody out there has got a 1 nanometer transistor. But at that point, the wires are so small and so close together that the electrons will tunnel from one wire to the next one. And that means that something that should have been a 1 comes out as a 0. The CPU is no longer deterministic. It's unreliable. You get wrong results. It crashes. All kinds of stuff happens. We can't make them go any faster. We can run more of them in parallel, which is where an awful lot of the kind of efforts and investment around parallel processing and asynchronous processing are coming from. But classical CPUs, I'm going to say this now, and I know there's folks recording this for YouTube, so you can come back and tell me I'm wrong. We are never going to see a retail CPU clocked at more than 5 gigahertz. It's just not going to happen because that is the sort of upper limit of how fast these things can go before the physics breaks down and stops working. But maybe we don't need to use classical CPUs. We talked about bits. 1, 0, true, false. A classical computer, everything is a 1 or a 0. That's how it all works. All the stuff we do with apps and Unicode and MP3 files really kind of boils down to 1s and 0s. Quantum computers are like, well, I don't want to decide, I don't want to make my mind up yet. How about we pretend it's a 1 and a 0 at the same time, and then when we know what the answer is, we'll go and fill the answers back in. Somebody once described quantum algorithms to me as, imagine flipping a coin, and then while it's in the air, you can stick another coin to it while it's still spinning, and you don't know which one's which, but you do know that you can stick it so that if that one comes down heads, the other one will come down tails. And you're like, does that? And yeah, it's a thing called the Hadamard gate. It couples 2 qubits while you still don't know their state, such that the state of one of them will influence the outcome of the other. And based on this, they've gone, well, if we could do that, we could do this algorithm, and if we do that algorithm, then we can factor RSA, and we can break public key encryption, we can do all of these astonishing things. And so quantum is potentially a game changer. Now, you can go out there right now, you can put your MasterCard in Amazon, and you can run Amazon Bracket, and they will give you space on a real quantum computer. Do Microsoft have one? I know that there's Q-Sharp. They've got actual quantum in the cloud. So if you are doing things like, nuclear reaction simulation, chemical simulation, you can go and you can buy time on quantum devices right now to run those algorithms. For most of the rest of us, we're not really interested in quantum. Not yet. It's interesting. It's exciting. It's probably not going to be relevant to the stuff we want to do with computers, because most of us aren't simulating nuclear reactions or doing protein folding, looking for new chemical compounds. We listen to music, and we take photographs, and we watch movies, and we check our bank balances and all this kind of stuff. And for the time being, classical computing is probably going to do a pretty good job on all these kinds of things. But let's backtrack a bit. I said a moment ago, a classical computer can represent the values 1 and 0. Now, 1 and 0 is an abstraction. The 1s and 0s don't actually exist. When I was a kid, this was my favorite show, Star Trek Next Generation, BBC 2, every Wednesday night, 6 o'clock, and the house where I lived was kind of on a hill, and the transmitter was on the other side of the hill, which meant we didn't get great reception. We didn't get very good signal. And so when the weather was bad, I'd get home from school and tune in Star Trek, and if it was very rainy or it was windy, the picture would kind of end up like this. Now, every single piece of that transmission process was analog. There were no 1s and 0s. There is a continuous wave like this of electricity being fed into a TV transmitter. That puts out a continuous wave of radio. That hits the antenna on the top of my house. That goes through a bunch of transistors and circuits and filters and diodes and ends up scanning an electron beam across the screen. So if you start messing with it, the mess is very, very smooth. It's very continuous. You get a sort of gradual degradation and a little bits of static strobing in and out. Now, if any of you has dimmer light switches in your house, these things used to work brilliantly because all light bulbs were incandescent. Light bulb has a little tungsten filament in it. If you put a little bit of electricity in it, it gets a little bit hot and you get a little bit of light. If you turn up the electricity, you get a little bit more heat, you get a little bit more light. You turn it up all the way, it gets very hot, it gets very bright. How many out there have tried low-energy LED bulbs with a dimmer switch? Because some of them work, right? But some of them, they don't know whether they're supposed to be on or off. Because a light-emitting diode is a digital device. It's either on or it's off. And so you turn the dimmer switch, and it's like definitely off. Yeah, kind of angry buzzing a little bit. You get in the middle, maybe, and then you turn it all the way up, and it's like, okay, now I'm definitely supposed to be on. But that range in the middle, a solid-state device like an LED, it does not know whether the wave you are sending it is a 1 or a 0. Now, that example there, that is the transition from analog to digital circuits. When television in the UK switched from analog to digital broadcasting, what happened is when you couldn't get a clear signal on Star Trek anymore, you wouldn't get kind of like wavy lines and static, you get JPEG noise. Because every single one of the pixels on your flat screen TV is being controlled by a circuit that's like, all right, a 1 or a 0. Well, actually, it's 8-bit color. So we have 8 ones or zeros on the red channel, 8 ones or zeros on the blue channel, 8 ones or zeros on the green channel. We have a whole bunch of processors and solid-state devices and chips and all these things. And because they are all digital, every single frame, every single pixel times 3 colors times 8 bits per channel is a component trying to decide whether the thing that just came through the rain out of the sky should be a 1 or a 0. And when they get it right, you get Star Trek. And when they get it wrong, you get Star Trek JPEG Compression Edition that you downloaded on your dial-up modem. Now, we live in a world of Unicode and APIs and .NET and cloud and Lambda and these wonderful abstractions. And, it is tempting to think, well, let's start digging. We chip away the layers of abstraction. We get down to ones and zeros. And we're like, this is it. This is the bare metal, ones and zeros. You talk to people who design circuits. You talk to people who design chips. They're like, no, ones and zeros is just a luxury abstraction. Actually, the whole thing that's going on is waves. It's all about waves, it's all about fields, and it's all about trying to figure out whether a particular electrical field at a certain point in time should be interpreted as a 1 or a 0. And the code that we build, we have unit tests, we have integration tests, we have continuous delivery, and then boom, it all falls over and crashes, and we think, oh, well, it's clearly not a problem. It works on my machine. It must be the hosting environment. Now, there was a perception for a long, long time that even perfect software systems were going to crash because of cosmic radiation coming out of outer space and zapping one of the bits in your memory bank, and that was going to crash your program. And this was sort of accepted wisdom, certainly when I was an undergraduate. 2015, a team at the University of Toronto did the first really large-scale study into the relationship between memory errors and system stability. And what they did, they got a bunch of crash data and memory usage data from some of the big supercomputing centers in the US and from companies including Google, and they basically analyzed the crashes, and then they went and studied the memory chips in the systems which had exhibited crashes. And what they found out is 1 in 10 of the systems in their study had had a serious fault related to memory. 1 in 25 of them that had actually crashed the system unrecoverably and needed a hard reboot. But when they then went and looked at the memory banks, they discovered that those banks were now prone to having more errors in exactly the same place or in adjacent locations, the same row, the same address column. Now, what do you think the odds are that a cosmic radiation particle from outer space is going to zap one of these things, and then 6 months later, it's going to go, oh, they've moved that chip to the University of Toronto. I'm going to go over there, I'm going to zap it again. It's not cosmic radiation. It's manufacturing faults. DRAM doesn't work. It's not 100% reliable. Now, the problem with DRAM is you can't fix it. The manufacturing processes, they spit out a 16 gig RAM chip, and it either works or it doesn't. And if it doesn't work, you're like, oh, well, that one doesn't work, throw it away. What semiconductor companies are trying to do to increase the yield on their manufacturing processes is they will manufacture a 16 gig RAM chip that's actually got like 16.1 gigs of actual space on it. And then if they find a problem during the quality control stage, they can patch that memory chip, that SIM or that DIM or whatever. They can be like, okay, that bank is bad, so reroute that bank to this spare one that we wired in over here, cut that one off, don't use it anymore. This works at the factory stage. Once the RAM then goes out into production, it's in your laptop, it's in your phone, it's in a data center somewhere, there's not a whole lot they can do about it. Now, there's a technique that is being trialed. It's been being trialed for a long while, which is called dynamic page retirement. NVIDIA is working on this on some of their high-end GPUs at the moment, and it's basically memory chips that kind of carry a spare tire. If they detect that one of the pages on that memory chip is no longer reliable, they will retire it, and they will swap in another one. Some of the strategies for this, Sun Microsystems had one back in 2004, an experimental system, where it didn't swap in another one. The RAM just got a little bit smaller, and a little bit smaller, and a little bit smaller. But this is based on the observation that most people would rather lose a couple of bytes of memory than have an unreliable chip running the system that their software is running on. Now, some of these systems, we are talking about mission critical. We're talking about important data centers where you have redundancy, you have all these kinds of things. We've seen that DRAM is not going to be 100% reliable. There's nothing much you can do about it. And even shielding it from outer space radiation is not necessarily going to work. And still, once in a while, you are going to have, there we go. I like the way my clicker failed at that exact moment. So for the rest of us folks out here building software for the real world, we can't really do anything about the RAM. All we can do is we can anticipate the user experience of what is going to happen when something doesn't work. We can think about, well, how can we preserve the user's experience? How can we make sure we still have their data? If they're in the middle of something, how can we make sure that next time they sign in or they reboot or they refresh the page, we pick up where they left off and they don't have to fill the whole thing in again? And this is about contingency planning. I've spent a large chunk of last year or the last couple of years doing remote talks and remote workshops from home. And I have backups for most things. If my internet drops, I have a 4G SIM card in my ADSL router so I can fail over to cellular networking. If my power to my house was to go out, I can run about 4 hours of stuff off my laptop battery tethered to my phone running off one of these battery packs. Now, if we get to a point, as kind of looked worryingly plausible for a little while there, and maybe still does, where they start switching off the electricity to large parts of London because they can't afford to run the generators anymore, I suspect we'd see a lot of people going out and buying these. UPS, uninterruptible power supplies. Basically a massive lead-acid battery that will run a couple of servers and things for a while. But worst case scenario, you know, if the power to my house goes out for an extended period of time, I'm just going to sit in the dark, you know. I sit and drink beer and light a candle and read a book and stuff. I grew up in Zimbabwe where we had probably 2 or 3 days a month, the power would go out for an extended period, like several hours at a time. And we lived with it, you know. We knew where the candles were, we knew where the flashlights were, we knew how to beat my mother at candlelit games of Monopoly until the lights came back on. This was inconvenient, but it was not a life or death situation. Now, there are applications where electricity is a life or death situation. There are hospitals, there are data centers, there are military command facilities, emergency services, places where they absolutely cannot afford to run on candlelight and papers until the power comes back on. Have you ever noticed red power sockets in hospital? The red ones are the ones that stay on. The red power sockets are the ones that are fed by the diesel generator that is in the basement. So worst case scenario, the power goes out, anything plugged into a red socket. By the way, you cannot use these to plug your laptop in to watch YouTube. They really don't like it when you do that. But most hospitals, they have generator facilities in the basement. They have battery backup. The batteries will keep them running until they can get the generators up. And the generators will keep all of those critical life support systems running for as long as they can get supplies of diesel. So in theory, they are self-sufficient on a scale of decades, assuming fuel supplies are still available. But right at the start of this talk, I said, you know, one of the biggest challenges we have around electricity is storing it. Now, sustainable energy is a big deal. It really is. And the tragedy of this, there is enough free energy. The amount of sunlight that falls on planet Earth in a given day is enough for everything that we need to do. It's just the wrong kind of power, and it's in the wrong place. The Sahara Desert, gigawatts of free electricity coming out of the sky that is absolutely no use at all if you are delivering groceries in Antwerp in the middle of the night in winter. Now, there is an argument which says that almost all the energy in the world actually came out of the sun in the first place, because we have the sun generates power directly, we have electric cars, we have solar-powered cars. There's a couple of prototypes of those been floating around the world. So if you are fueling or recharging your Tesla off the solar panels on your roof, well done you, that's an incredibly green and sustainable way to live. Just don't think about the manufacturing cost of the materials. Or sun comes out of, or light comes out of the sun and it lands on a tree, and the tree absorbs it, and photosynthesis turns that into sugar, and then a dinosaur comes along and eats the tree. And then the dinosaur falls over and dies. And then the dinosaur goes, and it turns into crude oil. And then we come along a couple of million years later, we dig up the crude oil, we refine it, we put it in the car. So technically all of us are driving solar-powered cars. But maybe there is a better way of using it than putting it in a tree, feeding the tree to a dinosaur, killing the dinosaur, waiting 65 million years, and then digging the dinosaur up and setting it on fire. This is the Desert Sunlight Solar Farm. This is in California. It's the biggest solar power station in the world. Opened in 2015. It generates enough power for 160,000 homes, but only when the sun is shining. Now, do people in California need a whole lot of power when the sun's shining? It's warm, it's bright, you don't really need heating, you don't need lighting. Laptops are kind of cool, and it's nice to have the internet. So last year, towards the end of last year, they installed this. This is the biggest battery in the world. This is a bank of about 20,000 Samsung lithium-ion battery cells, 230 megawatts of power storage. This will keep California's 160,000 homes going for about 4 hours. So the sun goes down, and if you needed to, you could run on battery until about midnight. After that, there's no more power. The thing that makes this useful is for picking up spikes in supply and demand, because one of the biggest challenges that we have with electricity infrastructure, the national grid supply, is that the demand for it is not constant. We're going to go back to the 4th of July, 1990, the Italian 90 World Cup. England are playing Germany in the World Cup semi-final. It is full time, it is extra time, it is 1-all. It goes to penalties. Chris Waddle steps up to take his penalty, and he misses. And he knocks England out of the World Cup. And 26 million people go, bollocks. And they get up, and they put the kettle on to make a cup of tea. Or they open the fridge to get a beer out. And there is about a 2.6 gigawatt spike in the electrical demand of the United Kingdom in the space of about 2 minutes. Now, we don't have that kind of electricity just hanging around because storing it is incredibly difficult. This thing is called a TV pickup, and it is one of the biggest problems of managing any kind of grid infrastructure. What happens when something happens that means a lot of people suddenly want a lot of electricity all at the same time? You have a massive spike in demand. Now, one of the best ways we found of storing electricity is we don't actually store the electricity. We use the sunlight to evaporate water. The water goes up the hill, it falls as rain, flows back down the hill, and then we go and we put a bloody great wall in the way and store the water behind it. This is Kariba Dam. It's on the boundary, on the border between Zimbabwe and Zambia in Africa. And this was built to provide power to the copper mines in the northern part of Zambia. It's one of the world's biggest hydroelectric power stations. But there are actually places in the world right now where when they have surplus electricity from solar, from wind power, from a hydroelectric, what they do with it is they use the power to pump the water back up the hill. It's called pumped storage hydro. So you have a bunch of water, you get a lot of sunshine, you're like, right, run the motors, pump the water back up the hill, and then if you need power in the middle of the night, you just open the dam, the water comes through, you can generate electricity on that basis. Now, the total amount of pumped storage hydro that exists in the world is about 180 gigawatt hours. That would run London for around about a day and a half. And that is by far the biggest store of energy that exists in any system anywhere. So if we had to run the whole planet on batteries and the stuff we've got backed up, our laptops would probably get us through to the end of the day, and then all the pumped storage hydro on the planet could keep London going until the end of the party tomorrow night, and then it would be game over. There is no more electricity. Storage is not going to cut it. We need ways of generating electricity sustainably and on demand. Now, a little while ago, I was down here. This is Dungeness. It's on the south coast. It's the only desert in the British Isles, and it is a weird place. And there are 3 things that you notice as you approach Dungeness. One, as you drive down towards it, or you cycle down towards it, as I did on this day, you see these huge pylons carrying high voltage power lines. Now, we've got good at building these things. There are power lines in China now which are carrying millions of volts, a couple of thousand kilometers. The second thing you notice is the wind turbines, because this is a big, flat piece of land right out on the edge of the country. They have very, very steady prevailing winds. It's fantastic for kite surfing and kite buggying, a lot of perks down there to do that. And then you get right to the end of Dungeness, and there's this, Dungeness Nuclear Power Station. Now, other than the one that I mentioned a second ago, how many of you can name a nuclear power station? Which one is it? Chernobyl, Fukushima, or 3 Mile Island? Or Sellafield, yeah, that one made the cut as well. The reason we know the names of these power stations is because bad things happened there, which has massively tarnished the reputation of nuclear power in the public eye. Now, there are all sorts of things we can learn from the circumstances surrounding what happened. You know, if you've seen the HBO miniseries, you'll have seen a fairly accurate dramatization of the corruption and the mismanagement around the way Chernobyl power station was being run. 3 Mile Island, similar thing. It was people cutting corners on safety checks. And Fukushima was an earthquake and a tidal wave at the same time, and it didn't actually melt down. It stopped generating power, and they had to go in and clean it up. But that was, you know, the scale of the natural disaster that hit it relative to the severity of the impact there. It's actually an astonishing piece of engineering. But The reason why stations like Dungeness are built way down on the southern coast, far away from anywhere, one, it needs to be near water, because that's the best way we've got at the moment. If you want to know more about that, go to Richard Campbell's talk on Friday, where he's talking about a thing called a molten salt nuclear reactor, which is just awesome. But at the moment, they tend to need to be near water, and people don't want them in their backyard. They want electricity, they want it now, they want it cheap, but they do not want nuclear power anywhere near where they live because they are afraid of it. So we put it out in the middle of nowhere, and the only way we've got of getting it from the place we generate it to the place where we need it is to build these big, ugly, monstrous, expensive pylons. And so every once in a while, the question comes up, could we do wireless transmission? Like, could we have the nuclear power over there, and we're over here, and we just kind of beam the power from there to there? Now, we can do wireless power transmission, about that far. We can do wireless charging of phones, and we can do wireless charging of electric toothbrushes, and we've got pretty good at these kinds of things. But we're talking about maybe tens of watts of power over a distance of a few centimeters. What we would really like to be able to do is to transmit electricity wirelessly over larger distances. Now, there's another NASA thing called the Power Beam Challenge, which is literally this. You have a robot, they have a cable hangs off a helicopter. Cable's about 1 kilometer long, and you have a robot that climbs the cable using power beamed from the ground. And the winning team, the last time they ran this in 2019, this robot in the picture climbed 400 meters up that cable using tight focus microwave radiation being beamed up from a base station. And they won a bunch of money from that, and they started a company called Power Beam Limited, who are now out there trying to do things with wireless transmission of electricity. But this is still a very, very niche, very specialist application. Now, we can transmit electricity through empty air, because if you crank the power up high enough, what happens is that you start stripping the ions off the molecules in air, and air becomes conductive. And when that happens, you get a spark. This is the spark you get when you push the button to light your gas cooker. This is the crackle you get when you plug something into badly earthed electrical equipment. This is how a Tesla coil works. Now, Tesla coils are really, really cool because they are things that literally make lightning. They are incredibly fragile. They are incredibly expensive. They use a lot of electricity. And the biggest one in the world is in a private collection in New Zealand. This is a picture of it. It can send electricity through the air a distance of around about 2 meters maximum. That's the best we've got, which is absolutely nothing compared to what nature does every time it gets a little bit weathery. Bolt of lightning can carry 30 million volts of electricity across a range of literally miles. Now, while I was kind of putting this talk together to deliver this week, I stumbled across a paper which I just thought was awesome. And it's early days, and it remains to be seen whether anything comes out of this. But there's a team in Switzerland just published a paper about using a high-energy ionizing laser to direct lightning bolts away from radio masts. Literally, they shine a laser up into the sky that is powerful enough that it ionizes a column of air. And they've got a photograph, which I do not unfortunately have in the deck, of a bolt of lightning going, oh dear, I'm going to go down there. That looks easier. So who knows? Maybe this could turn out to be something, maybe not. This literally paper was published on Monday. But I have always loved this idea, a bolt of lightning is absolutely awe-inspiring. And there is this wonderful quote about information systems and processors, which Daisy Owl tweeted a few years ago, which has stuck with me, which is, if you ever code something that feels like a hack but it works, remember a CPU is literally a rock that we tricked into thinking. Not to oversimplify it, first you have to flatten the rock and put lightning inside it. And so all of these systems that all of us work with, the mobile phones in our pockets, laptops, desktops, cloud, networking, all of this is possible because once upon a time, somebody looked up at the sky, they saw a bolt of lightning, and a little part of their brain went, I wonder if we could catch that and put it in a rock. Thank you very much.